Hello everyone, this is homework 3 part C. This time we're gonna be analyzing something that they call a rotometer. Hopefully I'm pronouncing that right. Let me increase this. Yes, okay. Um, so let me start sharing the screen and then you're gonna be able to see what I'm talking about here. All right, so basically a rotometer, what it is, it's this cylinder, let's say, and for this problem, we're gonna have a ball, okay, and the ball is gonna be somewhere here. All right, so we have inside that rotometer or that cylinder, whatever you want to call it, we have about three different cross-sectional areas. Okay, so we have the ball, which in this case is the same as the this part here because we don't want the ball to fall down. Okay, so depending on the flow rate, maybe the ball could fall down, but it would stop. So we're gonna say that, let me switch colors here. We're gonna say that this is and the same goes for the ball, okay? But in this area, we're gonna have, we're gonna call it Z, okay? And then, um, so should we call it D or D2? Let me see. Well, anyways, we're gonna call this area A1, okay? And it has a flow rate. The flow rate is the same because it's just one rotometer. Okay, so it's the same flow rate for every single one of them. We are going to have a difference in pressure. Okay, so P1, and then gonna call this P2. And we also have the cross-sectional area up here, we're gonna call A3. Okay, and we're gonna call this one down here A2. That's our cross-sectional area. And this also has our flow rate. Okay. From before, we know that our flow rate is Q equals a VA, which will come in handy later, not right now. As of now, we need to understand that the ball is kind of like steady. So let's say there's a fluid coming in uh, from down below, all right? And it's keeping the ball there. So the gravitational force that wants to pull the ball down goes against that fluid that's keeping the ball up. So we need to understand the balance of forces in here. So for that, we're gonna say that 0, just so it's balanced, is equals to, we have the density of the ball, okay, minus the density of the fluid itself, which we're just gonna say it's density, um, times that volume, so we can get the gravitational force. All right, so we have the volume, which in this case, I think it's pi d, I want to say cubed over 6. And this is all times gravity. So we have that. Besides that, we also have the pressure. So um, up here we also have, sorry, I forgot to add this, but up here we also have P3. Okay, so we need to account for those pressures on our balance equation. So we have P minus P3, or, well, the P1. Yeah, we forgot to define this. So we are using, this is our um, positive axis is pointing down. I mean, the positive direction is pointing down. So this is important to understand the problem. And that's why the density of the ball is positive. Okay, and the density of the fluid is negative because it's going up and down. So down is not, it's positive, therefore the density of the ball that's being pulled down by the gravitational force is positive. Okay, so the same follows for pressure, but I messed up here. I think should be P3 minus P1. Okay, so we have that, and now that's times our area, which our area, we're gonna say it's just our area 1, but we're gonna say over 4. Okay, so that's our area, and this is all equal to 0. Throughout this problem, we're gonna make a few assumptions. All right, first assumption is that our P3 equals a P1. So I'm gonna mark this up here. And again, this problem is, I feel like I didn't really explain what we're looking for here. We need to derive an expression relating the flow rate of the fluid and location of the spherical ball in a rotometer tube. So we need to understand the flow rate and then how time and height affects that and the location of the ball depending on the flow rate. So pretty much height related to the flow rate, like how much your flow rate is and where the ball is going to be. So we need to derive that equation or that expression. And for that, we need to consider, we also have to consider the slope, but that's going to come in later because the rotometer has a little slope here. Okay. So that does come in into the problem later on, but not for now. Let's just get the basics going, and then once we have that, then we can understand a little bit more about this problem. All right, so following on, we have if we are to say that, wait, sorry, this is actually P2. So this pressure and this pressure, they are the same. Apart from that, we're gonna say there are no viscous effect. It's written like this, viscous effect. So we are gonna be ignoring this. No viscous effect. I think I'm saying it right, but again, I might be wrong. Okay, so in this case, we could actually work this problem using the Bernoulli's equation. So if you guys remember correctly, we had density we had the difference in pressure. So we know that P3 equals a P1. So for the difference in pressure back then, we had P2 minus P1, but P3 is the same thing as P2. So we can just use that, okay? So we're gonna say P3 minus P1 over density. And then if you remember correctly, we also had the difference in our velocities over 2 equals to 0. And I think that's the only things for our Bernoulli's equation that we need to consider for this problem, because we're not going to deal with internal energy or heat or non-flow work in this case. We're just gonna, you just have a tube, okay, that has a slope, and you have a ball, you want to know how it works with the height. So we're not going to use the non-flow work. We're going to consider that to be non-existent, and there's no heat added to this problem, and no internal change in internal energy. Okay, so just going to work with the change in pressure and the change in velocity, and we're going to go from there. All right, hope you kind of follow. After that, we're going to kind of isolate P3 and P1. Okay, just because we have this here. So let's try to combine those two equations. I mean, why not, right? So if we were to do that, we would have P3 minus P1. That's equals V1 square minus V2 square over 2. And then that's times our density. So that's how it would look like. Furthermore, what we're gonna do is we're gonna put this on there. Okay, so that's what I was trying to say. We're gonna use P3 minus P1 equals that to put that into our original equation or expression. So let's do that. Okay. Yes, I am lazy when it comes to, because I mean, it's just easier, but you can write it down if you want, like old way. It's all good. It's all cool. V1 square minus V2 square over 2. times density. Okay, so that's what we have for P3 and P1. And I could use brackets for density, but I mean, it's all being multiplied. So I don't really see the reason to do that. Next thing, as you can notice, is that we can simplify a couple things in this problem. So let's go ahead and do such a thing. Okay, so first, this is gone, pi is gone, and we're gonna leave the fractions on there as of now, but eventually um we will change those, or should I? No, I mean, what's the difference? Why not just save us some time? So let's call this, let's divide it all by 2. So this becomes 2 and this becomes 3. Okay. So this is what we have as of now. Doesn't seem that much, that doesn't seem complicated at all. But again, things change. It might get a little bit more complicated than we expect, right? So the flow rate is the same for every single one of them, right? Like I said before. So Q1 equals A1 V1, Q2 equals A2 V2, Q3 equals A3 V3, and they are all the same. Okay, so let's just have that on there. With that in mind, we can say that A2 V2 is equals to A1 V1. And let's get, I think we should possibly do V2 by itself. Yeah, yes. Yeah, I mean, it looks a little complicated right now, but in reality, it's not really. Okay, so if we were to isolate V2 to make our lives easier, we would say that V2 is equals to times V1. All right, so like let's plug this on there, and I'm gonna move this around. So let's start from, let's add that to each side. So V2 square minus V1 square, oops, times density is equals to times G. We forgot the 1.5 here. Okay, so we have that. Now let's try to isolate V2, because we already know, actually we can just isolate V1. Yes, we can just use that as our V2. So in this case, we would have 1/4, which is just combining this, okay, times V2 squared, which is times our density, and this is all equal to okay. So let's move things around a little bit. First, I'm gonna do this real quick. So we have V1 square, and let's factor this out. So we have -1, and then we have 4/3. So just moving this 4 over to that side, and I'm gonna move this over to that side as well. All right, so we're gonna have Yeah, okay, times G. All right, that's what we have for now. Um, we we actually, yeah, I think we forgot this. Yeah, because this one was a square and that one is cube, so we still have a big one up there. So we need to account for that. So let's say this is actually DG. Okay. Glad we caught that. Glad we caught that. All right. So, if we were to move things around here, how would we do this? Say that V1 is equals to the square, big square root. So we definitely have the 4/3. We have and then that's all gonna be divided. Or is it just, I think, yeah, it's all gonna, well, since I can just, yeah, I think it's easier if I just divide this side, which is pretty much the same thing, right? I mean, it's Tom, so it doesn't really matter, but, um, uh, whoops. Okay, all right, so this is our velocity, but we do want to associate that with height. Um, Another thing we need to understand is that, so this ratio between A1 and A2 actually looks somehow like this. Um, you have, this is A1, and then you have the other part, which is A2. Okay, so the cross-sectional areas of A1 and A2, like A1 is much bigger than A2. That's what I mean by this, because A2 only has this, whereas A1 has all of this. Okay, so whenever we square that, this one is going to become irrelevant. So we can just go ahead and consider this to be 0. Okay. Um, Apart from that, we also need to, so if we were to understand A1, how could we possibly associate um A1 and A2 with the diameters? Because the diameters are actually going to be later on associated with the height. Okay. I mean, not the height, sorry, the slope. So we need to somehow using A1 and A2 associate that with the diameters. And the way to do that is to actually understand how those areas work. All right. So if we have A1 over A2 squared, what is that equal to? It is the cross sectional quas. Sorry, got something in my shoes. It's the cross sectional area. Okay, so it's the ratio between those two. So uh to do that, we're gonna have the first one, which we have established up there. I think we did some, yes, this. Okay, this is A1. So we have divided by what? Remember, as I said, A2, we have that difference, so that's what we have to account for. Okay, so that difference would be that little, the D, which is ball. Okay, so we have the ball. So d squared over 4 minus over 4. Makes sense? Makes sense? All right, good. So if that does make sense, let's move on. Let me just square this just so it is actually right. Now, if we are to associate those diameters with the slope, we need to start working on it. We need to start. So it first start with that little one, right? So little d, okay? And then you have your, it's the equation for slope is y so equals to mx plus b, right? So, I mean, that's where you can get your slope from. That's one of the expressions you can use for your slope. So we have d on there, and then we have our slope, and then our height. Okay, so we have b, and then we have m and x. All right, so those are kind of like core configurations. Now we notice that this d here is a square. Okay, so how would, I mean, little d, I mean, both these are square, but how would this look like if those two were square? It would look d squared, we know that, plus 2mh. It would just, I think it would be m squared h squared. Yeah, yeah. Sounds about right. Okay, so this is what we have as of now. So we already understand the velocity. We also understand how the cross-sectional areas relate to each one of them. We understand the diameters. So now let's jump onto our heights. Okay. So, but first let's solve for the areas, just because whenever we plug it in, if we plug it in like this, it's gonna look terrible. We don't want to do that. We want to make it as easy as possible, correct? So 2 squared is equals to, then this, so we already have that. I'm just gonna possibly just take this out. And we can also already kind of, since they're both multiplied by pi and divided by 4, let's just take this out. Let's just get them out of there. Okay, like get them out. So we did. Okay, and now we have a little more than I expected. D squared minus, which translate to this. Okay. Um, which will give us m squared, 8 squared, minus d squared. So you guys are gone. Now, we need to understand that for this rotometers, this slope is very small. It's not a very considerable number because it almost looks like a straight tube, but it's actually not, which could make some jokes about it, but I'm trying to keep it professional. So if the slope is very small and we're gonna like I squared that, it's gonna get even smaller. Therefore, we're just gonna call this 0 as well. Okay. So following that logic, if we are to throw this into the equation we had there, or the expression we had there. Come on, come on, come on. Okay. See, I didn't want to copy these, but okay. So let's delete all of this. And let's put her. Yeah, this should be square. Sorry. Over. Yeah. So there was, yeah. Yeah, I knew something was off. So this is actually, this should have a D here. Okay. I knew something. Okay, so boom, boom, you're gone. I mean, it's gonna be gone, but I knew that wasn't supposed to be a D squared up there. So, I mean, I practiced this problem before, I come out here and record it for y'all, but I still make mistakes, even when I practice. I mean, if you don't fail or if you don't make mistakes, then that means you're not trying. Don't know who said that, but it's very smart, and I think it's quite true. Okay, so we have that as of now. So now how do we relate that to the height? Um, sorry, I thought this is saying I had the wrong time on my iPad and I was like, what? It's 9:41. No, it's not. Okay, good. Yeah, it's not. Um, okay, so if we are to relate this to the height, this, oops, is what it would looks like. So height one, or I don't think we need to because we don't know what's gonna be, right? Um, okay. So height one, and then we had our uh densities. So density of the ball minus density of the fluid over density times do we still keep that on there? Uh I think we can kind of move things around here a little bit. We most definitely can. So the final expression for this, I'm just simplifying this on my head. Let's see. 16, 16. So this would be gone. I mean, it's not zero, it becomes one. Okay, so let me, because if I divide something by zero, then it becomes more complicated than I was expecting. Right? And I cannot do that. That just becomes one. Okay, so we already have our height. And then yeah, because we see like what we did here is we were trying to take this height out of there. We could just leave it there really, but I'm trying to take that out. Okay, so 16 m squared g. Could we have done that with t though? No, because that's, yeah, I don't think we could. Hold up. I'm seeing the easiest way to address this. problem. 16 squared g, we got the h out of there. And I'm thinking, yeah, we still have that 3, right? We still have that 3. Okay. Yes, and then so the 16 comes because we square all of this. Okay, so this becomes 4, and 4 times 4 is 16. And d is still being divided, so I think we divide it by 3d. So we still have this, this is, hold up, let me change colors. Let me just show what I was just thinking about. So this is the same, okay? Um, this is all square, so it eventually becomes uh we're this 2 eventually becomes 4, and we pass it up since it's dividing the denominator. So we pass it up. So 4 times 4 gives us 16. Okay. Reason being we are trying to get the h out of there, and that's what we were doing right here. So the 3, they remain the same. That remains the same. This remains the same. This is square, so this eventually becomes 1. And then d is just d, so or h is finally out here, which is what we were trying to do this whole time. And then we have our m, which is also being squared. So for our final expression, and the reason, like, we basically got the h, like we removed the h out of there before squaring that out, so that's why we don't have, I mean, we squared that, yeah. Yeah, since it's all being multiplied, if I wasn't to take the h out of there, what would happen is I would have this h squared. Okay, so it's still here, but since it's all being multiplied, I just took the h out, and this, whenever I squared, I take the square root, it can just come out like this, and that's what we're looking for. Okay, so I hope it makes sense. Again, just to recapitulate what we were doing. So this was all kept the same. All right. We're still dividing this by 3. So this is also the same. This one becomes d squared, and then d divided by d squared is just 1 over d, which is what we have here. All right. Once we have squared this bottom, the way, so we had over, okay, so this is what we had. So the way this looks is, so this goes away. So we will end up with g for m squared h squared. And since we're trying to relate the height to that velocity and the flow rate, because the velocity is related to the flow rate after all, we kind of just move this here, and it still kept the rest of our square root. And remember that we had that 4/3 times. I'm just doing this because I know I just did it now on my head, so I know it can be a little too much. Okay, this is gravity, and that's 4. So this 4 times that 4, that gives us 16/3. And then we have and that's all divided by d. So which is pretty much precisely what we had here. So this is how that equation works. So this is our expression. I hope it made sense. And thanks for watching. I'll see you on the next video.